Hello, welcome to lesson 2 on capacitance. Last time we looked at the first 3 points on the specification. Today we're going to be looking at parts D and E. The first one looking at the second equation for this topic, which looks at the physical structure of the capacitors. And then secondly, we're going to be introducing the idea of a dielectric as a material that fits between the plates and what it actually does and how that changes the performance of the capacitor. So to begin with, we're going to be considering what actually affects the capacitance. So the first thing that influences our capacitor is the area of the plates. We talked last time about how the plates are needed for electrons to flow onto them to create a charge on one side that repels the electrons on the other. The bigger the area, the more electrons you can fit on there and the more charge you can build up on a single plate. The second thing is the distance between the plates, or the separation. Obviously, if those two plates are a long way apart, the buildup of charge on one plate is not going to influence the other plate a great deal. So the closer together we can get them, the more influence there is and the stronger that capacitor will be. And the third one is the material in between. Now, we mentioned last time how on a standard capacitor we deal with an air or a vacuum in between the plates, and there is a value for those which relates to a quantity called the relative permittivity of free space. Now, permittivity is a term that means the ability to store electrical potential energy. Okay, so as I just went through, the area, bigger the plates, the more charge we can store, and therefore the capacitance is proportional to the area. The distance, the further apart the plates are, the less impact it'll have, so the distance is inversely proportional to the capacitance. And the third one, the permittivity, the higher that permittivity, the better the ability to store electrical potential energy. Okay, so the capacitance is proportional to permittivity. Those are the only three things that influence capacitance in terms of the physical structure of the capacitor, and therefore we can build an equation around those. So an equation is that the capacitance is equal to the relative permittivity of free space multiplied by the area, because those two things are directly proportional, and then divided by the distance or the separation between those plates. Now, the main mistake that people make on these is firstly rearranging correctly, which is always a problem for some, but secondly that they are quite small. Bear in mind your phones will have hundreds of capacitors in them, and therefore we need to be converting our data for the area into meters squared and for the distance into meters, but they are unlikely to be stated in those. So you need to do conversions for that data in order to get it correct. One reference for this is that generally speaking, capacitors will be measured in microfarads. So unless you're talking about something extremely large, or perhaps you're doing questions that I've made up and not done very good data, but if you don't get an answer in microfarads or near to that times 10 to the minus 6 sort of quantity, you've probably done something wrong, and it's probably due to your conversions or lack of them. Moving on, we're going to also introduce the idea of a dielectric. Now, a dielectric is any material that goes between the plates. So normally we have air or a vacuum, but we can replace it with pretty much any material. Now, obviously we can't use conductors, or that would just complete the circuit and the electrons would flow from one plate to the other. So generally speaking, we are looking at insulators for this. Common ones are wax, paraffin, acetone, okay, but there are lots of different types. Now, the purpose of the dielectric is to increase the capacitance. So we want materials that have a higher higher relative permittivity than free space, than air or a vacuum. Otherwise, we might as well just leave the air there and have that capacitance. There's no point reducing the capacity. The second option in terms of a dielectric is that we can use them to make them smaller. And this is how devices have become smaller over time. So if you needed plates that size with air in between, and you fitted a dielectric that had a much higher permittivity, that would mean you could get away with plates only that size. And therefore your device, whatever it is you're making, can become much, much smaller, particularly if, like complex devices, you're having hundreds of capacitors in there. So we need to be able to include our dielectric in our equation. So our original equation was that capacitance was equal to the relative permittivity of free space multiplied by the area of the plates divided by the distance between the plates. Now our first option for this is that if our relative permittivity is around the same value as our relative permittivity of free space. So if we have anything that is times 10 to the minus 12 farads per meter. It might be times 10 to the 11, might be times 10 to the 10, but you're in the same ballpark. Now, if that's the case, you simply replace it. So our equation will become that the capacitance equals the relative permittivity of the dielectric we're now using, multiplied by A, divided by D. Okay, so you'd be looking for values roughly around times 10 to the minus 12. The second option is when the relative permittivity is stated as an actual number. So you might have a relative permittivity of 3.5. Now, obviously 3.5 is a hell of a long way from 8.8 times 10 to the minus 12, our value for free space or a vacuum. And if that's the case, then you need to substitute this in next to epsilon O. So it would become capacitance equals EO multiplied by ER multiplied by A, then divided by D. Because if we were using a dielectric with a relative permittivity of 3.5, that would mean that the capacitance would go up by a factor of 3.5. So we need to keep the original EO in there as well. Okay, so you need to be aware that they can present that data in both styles. If you look online, if you Google relative permittivity of dielectrics, you should be able to find both types of lists. The most common is option 2, because that's far easier in terms of the amount of data being presented. You've only got to say epsilon 0 for free space, and then people who are using them know that they need to scale up. So just like in lesson 1, I'm setting you a task for using this second equation and introducing the idea of dielectrics. There's only 3 questions, but they do become more difficult as you work through, and there's subsections to each question. So the first one is essentially just using the equation. Second one then is introducing equation 1 as well. And then the third one is going through the idea of changing the size, changing the dielectric, and seeing what happens over time. Okay, so have a go at those questions, post them to me in the same way as you did for lesson 1, and let me know if you have any problems. Thanks.